Welcome back. This is Mr. Hassan's Maths channel. I'm answering a question here from the October 2021 paper from the Pure Mathematics 4 International A-Level Edexcel exam. I've actually answered this question some years back, and I answered this question using the traditional integration by parts method. All right, so I'm going to go through this because one student in particular has asked me to use the DI method for this and show how that works. Actually, it ends up being almost exactly the same as the traditional method for this particular type of question. But I'll show you how this is like, the second type of DI method type of thing. Now I call it the DI method or the DI layout because in fact, the DI method is integration by parts, just set out in a slightly different format. That's all. It's a bit more user-friendly for most questions, and so it's not really a different method. It's just a different layout of the integration by parts. So basically, we have to use integration by parts here because we have the product of two separate functions. Okay, and these two separate functions, x squared times ln x. Now, in order for us to integrate this, okay, one of these two terms has to be the part that we differentiate, and the other one we have to integrate. Okay, now there is a little kind of way of us memorizing, okay, how we can give precedence to certain types of functions for the differentiation part. So I'm going to have a column for differentiation and a column for integration. And basically, always logarithms take precedence over everything else. And then after that, you have inverse trig functions, which we don't really deal with. I think in Cambridge, they've started to introduce those in A-level now. And then we have algebraic expressions. Oops, how can I spell that wrong? Algebraic expressions, like polynomial equations, and polynomial expressions, and so on. Okay, and then we have normal trig expressions, and then we have exponential, like e to the power of something, to the power of x, and so on. Okay, so this is like the order in which you decide what to differentiate, okay, and what to integrate. So here we have a log expression and an algebraic expression. So we have a log expression and we have an algebraic expression. So the log has to be what takes precedence. Okay, it kind of makes sense because the one that ln x. I mean, normally you say, okay, x squared breaks down to something simpler, but the problem is we don't have an integral for ln x. So, and if we integrate ln x, which we can do using integration by parts, it becomes more complicated. If we differentiate it, sorry. If we integrate, it becomes more and more complicated. So if we choose x squared for this, it's going to make everything more complicated for us. So what we have to do is we have to choose ln x for d. All right, that will make it work. But that causes this to be something which is, almost the same as using integration by parts the traditional way. So we're going to start with ln x, differentiating it. And normally we differentiate until something becomes 0. But you'll soon realize if you try to do that, you differentiate ln x, you get 1 over x, which is like x to the power of minus 1. If you differentiate that, you get minus x to the power of minus 2. Right? You multiply by the power, take 1 from the power. That's like minus 1 over x squared. And if you differentiate minus x to the power of minus 2, you're going to get plus 2x to the power of minus 3. So you end up with 2 over x cubed. And you'll see it's going to get more and more complicated. It will never get to 0. It's never going to get to 0. So we have to stop there and say, okay, hold on. We can't do this in the normal way. This is like a second case of the DI method where the thing does not get to 0. It just gets more and more complicated. Right? There's another type where it keeps changing to give you the same thing again, just maybe with a different constant. Okay, and that's a third case that we're going to look at. Well, I've already got some examples in my playlist. But if this starts happening, you stop, you say, okay, let's stop. Okay, and let's just start integrating the other expression, which is x squared. If you integrate that, you're going to get x cubed over 3. X cubed over 3. And then when you see this happening, like it doesn't get to 0, you always check. If I multiply these two together, will I get an expression that I can integrate? If I multiply these together, I'm going to get x squared over 3. I can integrate that. If so, you stop and get rid of what you might have written below it. You don't need that now. And just like before, we put plus and minus. And just like before, we go diagonally down. So we have ln x times x cubed over 3. So we can say the integral of x squared times ln x with respect to x is going to be this times that, which is x cubed over 3 times ln of x. And then if we had to go horizontally across, if you have to do a product like this, then we have to integrate that product. So you're going to have minus the integral of 1 over x times x cubed over 3 with respect to x. Okay, and then that can be integrated and that will give us the answer. So you'll probably say, oh, hold on, that's exactly the same as just normal traditional method. And yes, that's exactly the same as a normal traditional method. Let me just get this ready. So this is going to be x squared. So now we can integrate that and we get our answer. So we end up with x cubed over 3 times ln x minus a third times x cubed over 3 plus c, which is x cubed over 3 ln x minus x cubed over 9, okay, plus c. And there is the answer, okay, which is exactly the same as what we got when we did the traditional method. Okay, so you can see that they basically look exactly the same thing. It's basically, we've done exactly the same thing, all right. But if you're using the DI method, the DI layout, if you normally this gets to 0, that's like the case where the DI method really makes a big difference, especially when you have double integrations to do stuff. It makes it very easy and neat and tidy. Okay, so it goes down to 0. But if you find the case like this with ln x, it doesn't come to 0, then you can go to the traditional method. You can use this. Basically, you have to basically just see when you stop when these two can be integrated. Okay, you stop when they can be integrated. When you find the product that can be integrated, you stop. And the third case is when you, for example, have e to the power of x and a trig function together, and you see that none of them breaks down to 0, but they kind of keep going through a cycle where they become the same as a question. Okay, and that's another case which you'll see if you check the playlist at the end of this video. Right, so that's just a short little video to explain how we could apply the DI method to this question. All right, so just to go through that. So I hope that was clear. Thank you for watching. Other questions from this particular paper, including the traditional method, will be found in the playlists that will appear at this part of the screen at the end of the video. Other questions from the topic of integration by parts. Okay, I'll have my playlist here, which involves the DI method specifically, and here I'll have a playlist dealing with all sorts of integration by parts. Okay, and you'll have here a playlist with different types of integration in P4. Okay, I hope that was clear. Thank you for watching and see you soon.